All right, so welcome to Math341, take 2, lecture 23, Monte Carlo integration, followed by the method of least squares. And so the idea is we're going to calculate areas, which is a very important concept, by throwing dots. And we're going to record what fraction of the dots land in the region, and that's going to give us a good estimate for the area. It's extremely important that you throw the dots uniformly. If you have a region like the question mark region where nothing is going, then you might have a very inaccurate estimation of the area. And this is just going to follow from the central limit theorem. So we're going to let the xk's be binary random variables. They're going to be 1 if you're in the region. They're going to be 0 if you're not in the region. And so we'll let x be the sum of the x1 through xn. And by the central limit theorem, this converges to being normally distributed. Now, this is not going to converge to the standard normal because I'm not dividing by the number of observations. So if I take x and I divide by n, then that should converge to a normal distribution, but that's not going to be converging to the standard normal, right? What would we have to subtract off? So what is the mean of each xi? So xi is 1 if you're in the region and 0 if you're not in the region. It's p. And what is p? Yeah, the area of omega over the area of A. So the probability that you land in omega is just the relative ratio of the area of omega to the area of A. If omega has relative size 1/2, then you would expect each xi to have mean 1/2. If it was 3/4, you would expect each one of them to be 3/4. So if I look at the sum of the xi's divided by n, that should converge to the area of omega divided by the area of A. And so it's not going to be converging to the standard normal. Not a big deal. We can just adjust. It's going to be converging to a normal centered at the area of omega divided by the area of A. Well, that's what we're trying to compute. We could adjust things, so that the variance is 1, but that's fine. The main thing to note is by the central limit theorem, we expect the variance is going to be on the order of, for the sum of the x's, how big do you think the variance will be? So we have n independent, identically distributed random variables. How big is the variance? It's the sum of all the variances. The variance of a sum is the sum of the variances if they're independent. And so whatever x1, whatever its variance is, it's just going to be n times that. So the variance is going to be of order n. So the standard deviation is going to be of size square root of n. So if you look at what we calculate when we look at the sum of the x's divided by n, we expect that to be of size area of A over omega. What about the fluctuations? Well, the fluctuations in x is going to be on the order of square root of n. We're divided by n. Square root of n over n, that's like 1 over root n, that goes to 0. So if you do this, you would expect the error term to be very, very small. As n gets larger and larger and larger, if n is 10,000, you expect the error to be on the order of 1 over 100. If it's 1,000,000, you expect it to be on the order of 1 over 1,000. We can easily get 1,000,000 dots for a lot of problems like this. Now, what is the actual variance? If you remember for binomial random variable, it's p times 1 minus p. So when is p times 1 minus p largest? When is your variance greatest? When they're equal, which is when? 1/2. So imagine you only have 2 options in life. And if you're a Seinfeld fan, there's a great episode of this, the opposite. You only have 2 options in life at every moment, and you always make the right decision. Is that good? Yes. What if you know you always make the wrong decision? Is that good? You can just do the opposite. So when you think about the internet and sending messages and error correcting, error detecting codes, you send strings of 1s and 0s. If you transmit information perfectly, that's great. If you know, however, that you always transmit the opposite of what you meant to send, that's also great because I know, I just flip it. The worst case is the 50-50, is you have a 50-50 chance of being right or wrong. You then don't know what to do. That's when the uncertainty is greatest. Same thing over here. The worst case for us is when the area of A is half that of omega. Okay. So we'll do the we'll do the method of least squares in a moment. What I want to do first is just do some computer code. And so I think I have to go through it like this. Okay. So, oops. Okay. So hopefully everybody can see the code. And then what we can do is, this is pretty straightforward code of throwing dots. Does anybody recognize the shape? Yeah, you shouldn't really recognize it. And so as the video plays, you should hopefully be able to identify it. It's going to send like the running area up top. Does this look familiar at this point? What does this look like? Circle of what radius? 1. And it's estimating the area as 3.11. And we've done 856 points. So really, on the order of 1,000 points, we're already seeing something pretty close to pi. And so I can let it run a little bit longer, throwing more and more points. It's really interesting to see, are there any giant areas of white? Are there any areas where we're just completely missing things? And I'll just jump to like the very end in terms of just how many dots it has. And then it becomes a really interesting question. What kind of clusters of missed areas do you expect? And you do expect that there will be some missed clusters, and you just hope that they don't strategically align in a bad place. There are ways to improve this. What we're doing is we're just throwing dots randomly, and we're just seeing how well we can do. If you know how much runtime you have, you can actually walk using the Fibonacci numbers, and then it will put the dots in a uniform grid where things keep getting rescaled. That's very poorly phrased. Let me do it better. Let's say you want to do a 100 by 100 grid. That's 10,000 points. That's a pretty good way to throw my dots. But now imagine you had an extra amount of runtime that you weren't expecting, and you can throw an extra 1,000 dots. Well, I can't just make that 100 by 100 a little bit larger now, because I would have to change all the relative grid sizes and locations. I would have thrown them very differently if I knew I had 11,000 points to do rather than 10,000. So the problem is, if all of a sudden you have a little bit more computational time, if I've chosen a fixed grid in the beginning, I'm now a little bit out of luck. I can still use them. I could maybe take a different grid and put them in that way for those 1,000, but it's not as good as if I knew from the very beginning. With the Fibonacci's, it turns out that the golden mean in some sense is the most irrational of all irrational numbers. There's a way to quantify that. And if you start moving along a line like Pac-Man, where when you get to one end of the board, you flow back to the other. By using the golden mean, you can just keep spiraling around. And then you just run it for however long you have. And it will keep putting the dots in essentially as uniform a manner as possible. And so it tries to minimize as much as possible having gaps like this. All right. I assume everybody here knows the area for the formula, the formula for the area of a circle of radius r? Pi r squared. And the circumference, pi 2 pi r. And it's actually coming from calculus. So you can actually see that by taking a circle, increase its radius by a little bit, subtract the 2, divide by, and you get that little area of that band, and that's where the circumference is coming from. Who knows the area of an ellipse? X over a squared plus y over b squared equals 1. Can you give me a case for A and B where you know the area of an ellipse? 1. Give me another case. A equals B equals. Right. And so you know that when A equals B, the area is pi r squared. What would you guess the area is in general? AB pi, right? It's the most natural thing to guess. It's got to be symmetric in A and B. It's got to reduce to pi r squared when A equals B. And so I have the ellipse x squared plus 4y squared equals 1. And just having it calculate. And just, again, very quickly putting in the dots. And so if it's x squared plus 4y squared, a is 1, and b would be 1/2. So pi ab would be pi over 2. Yeah, around 1.6 is not a bad estimate for pi over 2. And so this, I hope, shows you, I'll just try to jump to the end. And so this is, almost 7,500 points, 1.57. Double that, 3.14. And then we're supposed to get 3.1415. We have 463. That's not so bad. So again, Monte Carlo integration is an incredible technique to very quickly estimate quantities that you care about. We can't evaluate things in close. Now, is it possible that when we throw random dots, all of our dots land in the bottom left corner? Absolutely. So you can't use this as a proof. This is one of the reasons why flowing through the Fibonacci numbers or something like that is a much better way to do problems like that, because that will guarantee that you don't have something like this. That said, if you have enough data points, I'm really not worried about everything falling out there. Yes, it's theoretically possible, but we don't worry about all the air molecules coming to the front of the room and you all gasping for breath and time, right? We do not have a contingency plan for that, I'm sorry. It's just not worth considering, okay? But if you can avoid something like that without too much additional work, why not? Okay. So what I want to do now is I want to move to, just the right one. No. Okay. And then I don't think it's showing in Zoom yet, so. All right, so it should be sharing in Zoomland now. If you don't see it, let me know. Or actually, if someone can just put in the chat, do you see it right now? It should say Lecall data, LeastSquares. Can somebody let me know in Zoomland that they're seeing this? Yes, okay, thank you. Okay, so what I want to do now is I want to talk about the method of least squares. This is one of my favorite applications of not just stuff that we've done in this class, but the prerequisites. Linear algebra was a prerequisite. Multivariable calculus was a prerequisite. We should be using those. Okay. So what does this look like? A line. What is really bad about this plot? Okay, why is that bad?
Why? Oh, I thought it was one is going like lower to higher to lower.
No, they're both going low to high. There's something really bad about this plot. Yeah. There's no labels. You need to put in labels. I saw a great graph about some point in the past about how gas prices are going down. They zoomed in tremendously and hid the scale of the axes to make it look like there was a massive change. You want to be very clear about what am I even studying here? I don't know. It seems like there's a linear relationship between them. If you had to guess, what would you say is the slope of the line? Just as a quick guess. 4, why 4? So if we go up 20, we go over, but if we go up 20, we go up to about here, which is about 100. Right? If the change in x is 20, it looks like we're going up to something about height 100. Yes? No? So what would you guess for the slope? I would guess 5. What would you guess for the intercept? Maybe 0. Which are you more confident about, the slope or the intercept? Slope. For a lot of things, the slope is more important because we care about what's going on as we get further and further out. A small little error in the slope is not going to make a huge difference far out. But a small error in the intercept is not going to make a huge difference far out, but a small error in the slope is going to compound. So if I had to choose which one I care most about, typically I would choose the slope. So this was coming from Spring Data. If you're an XKCD fan, wonderful comic strip. This is a really nice one. And if you hover over an XKCD, it gives you additional text. And this one is, I think, quite amusing. All right. So I was looking at fake data from a spring. So hopefully you've done enough physics to have seen, Hooke's law, that the force is proportional to the displacement when you stretch a spring, at least for small displacements. And so I took the fictional, y equals 5x, and I put in a little bit of random fluctuations so that, you have some simulated data. And so let's talk about how we would find the best fit line to something like this. Skip that right now. So the idea is we want to find the best fit line. How do we find a best fit line? Well, if it's best, it has to be best relative to something. I need some metric, right? If I want to say you're best with respect to what metric? Here are three possible ways to measure errors. I could look at yi is what I observe, and axi plus b is what I predict. And I can look and see what's the difference between observed and predicted. That's the first. I can look at the absolute value of observed minus predicted, or I could look at the square of observed minus predicted. Two of these are legitimate metrics. One of them sucks. Which one sucks and why? Yeah, first one sucks. We don't have to be polite. Why does it suck? Yes. So imagine I give you two data points, bottom left corner and top right corner. What's the best fit line through bottom left corner and top right corner? Is everybody getting a diagonal line going from bottom left to top right? If I use the first metric, I could go from top left to bottom right, and the two errors would perfectly cancel. In fact, I would have infinitely many lines that would have zero net error. In fact, it's very easy to get almost, to just tweak things a little bit and get zero net error. What does a negative error even mean? So the first one is really bad. You should not have errors being able to cancel with errors. For some things in life, yes, you can overshoot and then sure. But in a metric of trying to see how good things are, this is really bad. What is the advantage of the second over the third or the third over the second? Why is the third one computationally clean? I have to square things rather than just drop a sign. But I mean, you give me a function. If I want the absolute value, I just drop the sign. That's easy. Gone. But this one, I have to square things. That's more computation. How many of you have seen linear regression before? How many of you have heard why we do the third over the second? Or this was just, and Moses came down from Mount Sinai, and on the back of the Ten Commandments, there were also, thou shalt be comfortable using the central limit theorem when n equals 30, and thou shalt use sums of squares for measuring errors. Okay.
Is it math?
Yeah, but is that a good thing or a bad thing? So imagine you're collecting data, collecting data. Collecting data. You have one bad observation. And that one bad observation is now going to have a huge impact because you magnify errors. So ideally, you don't want to have any bad observations. If you have a bad observation, you want a reason to justify throwing it away. When I took psychology at Yale, it was mandatory that you had to participate in psychology experiments. That's how they got their people. I'm not going to say this while it's being recorded, but I am quite proud that they had to throw me away as a data point on one of the experiments. And they had to justify why they removed me. But is that good or bad that it magnifies? You were somewhat on the right track when you were talking about differences between the absolute value and the square function. The absolute value is easier to work with. But there is an advantage the square function has over the absolute value function. And it was similar to the piecewise. It's differentiable. How many calculus classes have you taken already? 3, right? Don't you want to use those classes? Or is this, I suffered through it already, checked off the box, don't ever want to revisit? No, there's a reason why we had you take all those calculus classes. We're now going to get dividends from it. And in fact, we need multivariable calculus. So the advantage of 3 is that it's differentiable and the tools of calculus are available. The advantage of 2 is that one bad observation doesn't have as much of an impact. So the way I like to phrase it is, if you hire me, I like to use 3. If I hire someone, I like to use 2. I like them to use 2, okay? Now, what's nice is if we use 3, we're going to be able to get a closed form expression for the answer, for the best fit parameters A and B. And so I apologize for insulting you by reviewing linear algebra that you know so well. But let's just make sure everybody's on the same page. Let's review some linear algebra and let's review some multivariable calculus. I believe I ran into the door earlier this semester, yes? Why did I run into the door? What was I trying to remind you of? When you're doing optimization problems, what do you have to remember? Boundary conditions. So we're going to try to find what values of A and B minimize the total error. I'm not going to really have to worry about the boundary conditions because I can let A and B go off to infinity. And as A and B get larger and larger and larger, clearly I can just run up the arrow. So I know that the best fit line is going to come from, some A and B in a nice box. I know that I just have to find where the partial derivatives are 0. Why do we search for where the partial derivatives are 0? If the partial derivative is not 0, then if I move in that direction, I'm increasing or decreasing, so I can't be a maximum. If the partial derivative is positive, I get larger if I move in that direction, I get smaller if I move backwards. So as long as I'm at an interior point, the only chance I have to be at a critical point, to be at a extremal point, is to be at a critical point. I need the partial derivatives to vanish. It's important to remember the difference between a necessary and a sufficient condition. Can somebody give me a necessary condition to win the Super Bowl? Be in the Super Bowl. Is that a sufficient condition? No, you can ask Professor Blackwood, who is a Bills fan. They have 4 straight years where they made it to the Super Bowl and did not win. Okay. What is a necessary and sufficient condition for winning the Super Bowl? Scoring more points. You score more points and you win. Is there any way to win the Super Bowl without scoring more points? I don't know if the commissioner can, in the middle of a game, declare that the other team has done so many bad things that we're calling the game even. It seems like that would be a nice, necessary, and sufficient condition. So over here, if I want to find candidates for the best fit line, I look to see where the partial derivative is 0. That doesn't mean that that is actually where the minimum or the maximum happens. These are the candidates. Okay. Do you remember your second derivative test or your first derivative test to see if you have a maximum or minimum? You can do stuff like that. From physical grounds, I know that there has to be a best fit line. It may not do a good job, it may suck, but there's got to be something. And the reason is I can assume A and B are in a nice closed box. And in real analysis, you will learn a beautiful theorem. If you have a continuous function in a box, in a finite box, then it attains its maximum and minimum. In an open box, that's not true. I could give you the function 1 over x, which is exploding as I go to 0. That doesn't attain its maximum. But if I have a nice continuous function on a closed box, it attains its maximum and minimum. So I know there's going to be a choice of A and B in the box that will give me my smallest value. And so all I have to do now is I just have to take the derivatives. Okay, and so I thought, okay. So as I said, does this notation look familiar? Gradients, remember that? So I have the vector dEdA, dEdB. I want that to be 0, so I want each one of them to be 0. As I said, I don't have to worry about the boundary points. So now when we take the derivative, if If I take the derivative with respect to a, the 2 comes down. I get yn minus a xn plus b times negative xn. Something similar when I take the derivative with respect to b. And so now I have 2 equations and 2 unknowns. Well, when I look at them, I can divide through by 2, or by negative 2, that doesn't really matter. And now I have 2 equations and 2 unknowns. What are my unknowns? So what are the unknowns we're trying to find? No, I'm sorry. A and B. A and B are the unknowns, not X and Y. The XNs and the YNs, they're known. The XNs are where we make the observations. The YN is what we see. We're trying to find A and B. So we have 2 equations and 2 unknowns. Should we be able to find A and B with 2 equations and 2 unknowns? We're basically looking at the intersection of 2 lines. Do 2 lines always intersect? No, right? They could be parallel, or they could even be a special type of parallel. They could be the same line, in which case you could have infinitely many solutions. So the hope is that there will be a unique A and B. So we just have to solve this. It doesn't look like your standard linear algebra equations because you normally have it say maybe ax plus by equals c, dx plus e, something like that. So I can just regroup things a little bit. For the first equation, I pull out the coefficient of a, I pull out the coefficient of b, and then I do that same for the second one, and then I move the constant term over to the other side. So what's nice is I can write this in matrix form. The sum of xn squared is the upper left, then the sum of xn is the top right, bottom left, and then the sum of 1 is the bottom right. How would we solve this matrix equation? What should we do? You multiply by the inverse of the matrix. Is every matrix invertible? So we hope that this matrix is invertible, and if so, we can solve it. If you're not comfortable doing a matrix inversion, we could just go back to this equation and then just solve for A in terms of B from one equation, substitute that into the other equation, and then solve for B, and then now that you have B, then you get A. So if you don't remember how to do matrix inversion, we're fine. As a quick review, there's a nice formula for the inverse of a 2x2 matrix. And so, it's not so bad. So we take our matrix, we assume it's invertible, and then that gives us an explicit formula. Now, what's nice is, unless you're a complete moron as a scientist, your matrix will be invertible. You have to really work to choose data so that this is not invertible. And this is where it's incredibly useful to be able to do some basic algebra. What's the determinant of a matrix? That measures whether or not it's invertible. So if the determinant is 0, it's not invertible. If the determinant is non-zero, it's invertible. So the determinant is the sum of xn squared times the sum of 1 minus the sum of xn, sum of xn. Well, the sum of xn is almost the mean. If I just divide by capital N, the number of data points, then that's the mean. Okay, so I can't just divide by 1 over n, but I can if I multiply by n. So the sum of xn, that's the same as n times the mean squared. And now the other one is n sum of xn squared. So I can pull out an n squared, and I get 1 over n when you do a little bit of algebra, the sum of xn minus x bar squared. What does that quantity equal? This is a quantity we've seen many times. The variance, right? There's 2 ways to calculate the variance. It's the expected value of, xi minus the mean squared, or it's the sum, it's the second moment minus the square of the first moment. That's how I can do this algebra and say, oh, it's just the sum of xn minus x bar squared. So the only way this matrix is not invertible is if the determinant is 0. And the only way the determinant is 0 is if the sum of xn minus x bar squared is 0. What's the only way a sum of squares can be 0? So I have a bunch of real numbers. All of them. All n have to be 0. So do you agree that the only way this is not going to be invertible is if every xn minus x bar equals 0? What would it mean if every xn equals x bar? They'd all be equal. So let's imagine that you want to be a scientist and you believe y depends on x. So you want to figure out, how does y depend on x? I'm going to gather data. And to figure out how y depends on x, I'm always going to use the same value of x. And I'm going to try to sniff out the x dependence by always looking at the same value of x. You're a moron. There's no polite way around it. You should not be allowed anywhere near a lab. Right? If you want to see how it depends on x and you don't vary x, you're stupid. As long as you let the x's vary even a little bit, then the determinant will be non-zero and this will work. So it's not an issue at all, but it is something that should be proven that this method will work, and it can be done. Okay, so there's lots of different ways of writing down what the formula is depending on how you want to store things. Any way you want to do it is fine. What's nice is it's a closed form expression. You give me the data and I can just immediately write down what A and B are. And sometimes it's nice to introduce, auxiliary quantities to express things in terms of variances and whatnot, but it doesn't really matter. Here's a particularly nice way of just writing down what the A's and the B's are. And so you don't even need a complicated program. I mean, I will do this for you immediately. Google Sheet, Excel, they would do this for you very nicely if you have your columns of X's, Y's, and then you multiply xn squared, xn, yn, all that. Very easy to get these. These formulas are also reasonable. So one of the things I always like to do is unit analysis. So when you're looking at things like this, let's say X is in meters and Y is in meters squared. Then to go from meters to meters squared, A would have to be in meters, Y equals AX plus B, and B would have to be in meters squared. So you want to see, would A have units of meters? And you start going through and seeing what would you get. Well, if yn is meters squared and xn is meters, this would be meters cubed. This would be unitless. The xn would be meters. This would be meters squared. So the numerator would have units meters cubed. The denominator would have units meters squared. Good, it would divide out and it would give me A would be in meters. So you can do quick checks like this to see, is the answer reasonable? And again, it's so easy to make a mistake like this. It's not going to catch a mistake like a minus sign versus a plus sign. But just the expressions you have here, all of these expressions have the same dimension. That's good. I shouldn't be combining things of different dimension. Okay, this is just, quick review. If you are uncomfortable with matrices, one of the ways we often handle systems of equations is you multiply the two so that they have the same common value, then you subtract, solve for one, substitute, solve for the other. But again, 21st century, no one does this. Your computer will do this for you. Okay. Most things in life are not straight lines. So if we could only handle straight lines, we would be in trouble. So one thing is, it actually doesn't matter that it's a straight line. What matters is that we have a relationship that's linear in the unknowns. We did A and B, and we did Y equals AX plus B. So that's the case, F1 of X is X, and F2 of X is 1. More generally, I could say I believe Y is this linear combination of some functions F1 through Fk. So this is something from linear algebra, looking at linear combinations. And as long as it is linear in these combinations, the functions F1 through Fk don't have to be linear. They could be exponentials, logarithms, trigonometric, whatever, as long as it's a linear combination. Now, can somebody give me a famous function from physics, a relation from physics that's not linear? So yeah, Hooke's law would be linear. What forces do you know from physics? What's your first go-to force? Gravity. So what's the gravitational force between two masses? This is G m1 m2 over r squared. So the force is proportional to the product of the masses and inversely proportional to the square of the distance. So if I double the distance between them, the force is 1/4 as strong. Why is it a 1 over r squared force? Well, there's actually some really nice geometric arguments. The surface area of a sphere grows proportionally to r squared. And so if you imagine that, you have your force in the center exerting some kind of yankage that is pushing this yankage out. And the further out you go, it's being spread out over a larger and larger sphere. So in order for the yankage to be constant as you go further and further out, the force of the yankage per each square unit has to be decaying like 1 over r squared. So when you multiply it by the surface area, 4 pi r squared, you get something that's constant. So it's a nice geometric reason as to why gravity might be a 1 over r squared force, but that's not necessarily an argument that works. So in this class by now, you should know we take logarithms. Right? When in doubt, take a logarithm. So Newton's law of gravity. Imagine we didn't know that it was r squared in the denominator. Imagine we thought force was proportional to the radius to some power a. Well, if we take logarithms, then we get the log of the force is a log r plus b, where b is the log of big B. Now we're in a situation where we can use the method of least squares, where we can use linear regression. So we didn't initially know that it was a 1 over r squared force. We thought it was proportional to r to some power. We didn't know what that power was. But by doing a logarithmic change of variables, we're now in a situation where we can use the method of least squares. And we can try to figure out what is the best value. Now, how many people remember any of their physics? Does the Earth go around the sun or the sun go around the Earth? Earth goes around the sun. Actually, the Earth goes around some kind of common point, but it's dominated by where the sun is. So Newton was led to his great results by work of others, experimentalists who gathered data and people who started to come up with some laws of motion. So Kepler came up with 3 laws of motion. The first is planets travel in elliptical orbits with the sun as one of the foci. The second is if you draw a line from the sun to your planet, it sweeps out equal areas in equal time. And then the third, this is lovely, is I believe it's either the square of the period is proportional to the cube of the length of the semi-major axis, or I've mixed up my cube and my square. Let me do Kepler first. Oh, okay, yeah, so here's Kepler. Okay, so yeah, I was right. So the square of the period is proportional to the cube of the length of the semi-major axis. So Kepler got this by looking at experimental data. That's amazing to get this by looking at experimental data. So I've got this relationship t squared the period equals b tilde L cubed. Why would I call it b tilde? I'm calling it b tilde because I'm not going to keep it for long. What could I do to both sides? I could, and I will take logs. And again, that's not a bad thing to say. But there's something I can do before I take logs. There's another operation. I have t squared is b tilde L cubed. So if I were to try to figure out what the exponents were, do I want an exponent on both t and L? What should I do? Yeah, take the square root. That's why I have it as b tilde. So when I take the square root, Kepler's law becomes the period is equal to some constant times the length to the 1.5. This way you can write out without using fractions, but I don't really have 2 free exponents. And again, you always want to get a sense of how many free parameters do you have that you're trying to solve. I have 1 free parameter, the exponent of L. Or I can have it, the free parameter is the exponent of t, doesn't matter. But I don't have 2 free variables from both of them. So the variables I have that I'm trying to figure out is what is that constant b? And what is the exponent of L? Now we take logarithms. And so before we do that, I'm assuming most people do not know the distances from the planets to the sun. So I have recorded that for you, and I've recorded the orbital periods. I am using astronomical units to measure the distance. So 1 astronomical distance is the average distance from the Earth to the sun. Looking at this data, can you approximately tell me what B should equal? So if T is supposed to be B times L to the A, Is there any planet that could help us figure out what B should be? Right? Look at the units we've chosen. I'm measuring things in astronomical units and years. In those units, the period should basically be 1 and L should basically be 1. So I'm choosing good units. Have we talked about units like the Bruno, the millihelen, the slug, the smoot? Have we done any of these? We've done the smoot, right? Have we done the Bruno? I'll let you look up what the Bruno is. These are some fun ones. And so if we look at the log of the period against the log of the length, it is an incredibly beautiful straight line. And if you want, you can actually do the calculation. The data is not that hard to play with. And this just really shows you the power of looking at the data in the right way. It's very hard to see nonlinear relationships, but often when you do a log-log transform, the data becomes linear. So going back a little bit, so I forget what year this was from. Again, great example of why you never have things without labels. This was from one of the first lectures I gave on the subject. I can approximate when it was, but this is the 25 most populous American cities from some time in the past. And if I plot them, that's the relationship. It's the plot of the rank versus the population. Can anybody tell me what curve that is? Not really. If I plot the rank versus the log of the population, can't really tell. But if I plot the log of the rank versus the log of the population, that's actually not too far off from a straight line. And so if I try to do the best fit straight line, I think this was with 100 cities, so I got more data points. It's actually not that bad. This is word counts of most populous words. And again, it depends which data set are you taking. Are you using highfalutin English? Are you using street English? Are you using English in movies, English in literature? But when we do a log-log plot, it's actually pretty linear. And so whenever you're learning something, you always want to ask, what is this good for? If we can only do linear relationships, most things aren't linear. But with change of variables, a lot of nonlinear things can become linear. So I'll just do one last example, and then we will play a game for the rest of class. So I have served for over a decade on the Mount Greylock Regional School Committee. Initially, we were 3 school committees. There was one for the middle high school, there was one for Williamstown Elementary, there was one for Lanesboro Elementary. How many school committees do you think we needed for 3 school districts? Each was a separate district. How many school committees do we need? 3. We actually had more than 3. Each elementary school had a committee. The middle high school had a committee. Then there was a committee of people from both elementary schools. And then there was a committee with people from that committee and people from the middle high school, because we shared some resources. So we actually had, to some extent, 5 committees. We decided to fully regionalize the school districts of the 2 towns. And our budget is, say, on the order of $20 million a year. We get about $3.5 million from the state in Chapter 70 funds. When we were 3 school districts, the state told us how much money went to each building. But once we became, or if we become a region, they will no longer tell us how much goes to each building. They only tell us how much goes to the district. And we needed to figure out how to properly assign the money to the 3 buildings. The state kept their formula secret. So the question is, could we use linear regression to estimate the state formula and properly divide up the money? And so we want a formula that is fair, that does a good job predicting. Sometimes it's not enough to be fair, it has to seem fair. I remember one year, my daughter wanted to be the leadoff hitter in baseball, and my son wanted to be the starting pitcher. And I was coaching my daughter's team, and somebody else was coaching my son's team. And I told my son, you will be the starting pitcher because it's either you or the coach's son, and he doesn't want to look like he's playing favorites. And I told my daughter, and that's why you won't be batting first. Things need to seem fair. It's extremely important when you're discussing things that it doesn't look like something is being hidden or going on. And the other thing is you want a formula that can be explained. You have to be able to explain this to the select boards, to the finance committees, to the voters. I'm not going to ask if anybody here has counted cards. If you are interested in stuff like that, I obviously do not know any Williams students that I can connect you with. But one of the games people often like to count cards in is blackjack. And they like to keep track of a lot of high card values gone out or low card values gone out. And for a lot of the professional card counters, they don't use the best algorithms and formulas. They use formulas that they can do very easily without it looking like they're counting cards. And so you're willing to trade off a little bit for ease of use. And this is something to think about when you're coming up with a formula and a proposal. What do I want to do? Is a little bit of a gain here with the added complexity and then getting this by various people and explaining things. So we actually use the method of least squares. We use really only two inputs: the populations of the two towns and the assessment of the towns, the property values. And so, properties we wanted the solution, we wanted to exist. We need to figure out how much money to allocate between the towns. So it should be between 0 and 1, it should add up to 1 when you go over the 3 schools. We want it to be stable under small changes. If you add 1 student, this shouldn't be a massive change. That almost happened for one of the state formulas with Pittsfield a couple of months ago, is you get a certain amount of money if you have a certain number of students in a certain category of economic disadvantage. And Pittsfield was potentially like 2 kids below what they needed. And they could lose millions of dollars in funding. Now, you might say, if we're going to lose millions of dollars of funding and we need 2 more people in a certain level, and I'm not going to say more than that, it turns out that they had miscounted how many people there were and they were fine. But when you have formulas with sharp cutoffs, this is a real danger. You should not be losing millions of dollars if you have 1 or 2 students either move in or move out. And so we wanted a formula that would be stable under small changes. And so it turns out that we were able to do this. For the most part, there really wasn't tremendous amounts of fluctuations. When we actually ran things, we were essentially within $10,000 for each school. And so we made the predictions before the state came out with their numbers, before we regionalized. And this was one of the things that allowed us to go forward. And every year now, the school district has to calculate a linear regression to estimate how to allocate the funds. Okay. And then what I'm going to do now is I'm going to stop the recording.